Alright, welcome to this Scribblecast on nonlinear system of equations. The outcomes we have today are to look at graphing nonlinear systems, solving them, and perhaps looking at some applied problems. Perhaps let's start there. One of the purposes of using system of equations is to be able to solve a problem like this one. I've got a question where sub sandwich shops sells small and large subs. Customer buys one small sub and he buys two large subs for $10. I put X in and Y in for the price of small, price of large. Another person buys two small subs and buys one large sub and it costs him $8. So what are the price of the small and the large subs? I could use system of equations to help me solve that problem. Here's another one, interesting problem. I've got the Earth that has a particular orbit. Perhaps it's an elliptical orbit. And maybe I have some other kind of heavenly object like a meteor or an asteroid, and I'm wondering if that's going to collide with the Earth. Well, if I can define the path of the meteor, and if I can define the path of the Earth, which I know, I can use system of equations to help me solve that. I might have one path that looks like that, another one path that looks like this. And if those two paths are going to cross, something's going to give. There will be a collision of some sort. When we've done system of equations in the past, specifically just linear functions like these, we've used two or three methods to solve them. One of which would be a graphing, so I could graph them and find out where they cross. Another one is substitution, and the other one is elimination. Elimination is sort of my favorite. But let me show you just quickly how you approach each one of those. This is a review, you've done these before. But substitution, in order to do that, if I have a system of equations, a line and another line, I want to know where they cross. What I can do is take one of the equations, I'm going to take the second one, and solve it for one of the variables. In other words, get x on a side by itself. Once I have that, now I'm going to take the value of x and substitute it in for x everywhere I see an x in the other equation. So I'd have 2 times negative 3y plus 2 minus 3y is equal to 7. Then I'll proceed to solve that equation for y. So I'll get minus 9y is equal to 3. Divide both sides by negative 9. I get negative 1/3 for y. Then I'd take this value and plug it back in for x, either in this equation or this equation, or plug it back in for y, either here or here, and solve for x. Then what that does is it gives me a point. I have a y value, negative 1/3, and I have an x value from me plugging that in. Graphically, it looks like that number is 3. And there I have the point at which those two lines cross. That is by using the substitution method. The elimination method, I'm going to get the same result, but a slightly different way. Here's my two equations. In elimination, I look for either the x value or the y coefficients to be the same number. If they're not, I can multiply whole equations by a number so that the coefficients are the same. In this case, I've made it so that the y values are both the same, negative 3 and positive 3. If the signs are different, I add the equations. If the signs are the same, I could subtract the equations. So 2x plus x is 3x. Minus 3y plus 3y gives me 0y. And then 7 plus 2 is 9. Solving for x, I get x is equal to 3. I look at my graph, sure enough, 3 makes sense. And I can plug the 3 back into either one of those equations and solve for y, which I would put as the second part of my coordinate there. So that's a quick overview of elimination. So what we want to do is be able to take those two strategies and solve non-linear system of equations. Like here I have two ellipses, where do they cross? Looks like there's four answers. A parabola and a hyperbola, where do they cross? A circle and a line, where do they cross? And that's what we'll solve today. And we'll use the same processes as we've used with the others. So here's an example. This first one is a hyperbola. The hyperbola, I believe, would look like this one, something like that. And here I have a straight line. So I have a straight line, and I don't know how it would look. Maybe it crosses something like that. I don't know. But there's a chance for it to cross in a couple of spots. There could be more. Could just be one, but there could be more. Okay, so in this case here, I have an x squared here, but no x squared there. Trying to get my coefficients the same isn't bad, but if I have an x squared and I'm needing an x squared on the bottom, it's quite difficult to do that. So typically in a case like this where I don't have x squareds and y squareds lining up, I'm going to solve this by using substitution. So I'll take this second equation and I'll solve it for y. We'll call that equation number 2 and this one 1. So equation number 2, I solved it for y. Now I'm going to take that and plug it back into equation 1. So wherever I see a y, instead of a y, I'm putting in an x plus 2. Okay, in simplifying that, I'll FOIL this out. It's x plus 2 times x plus 2. So it's x squared plus 4x plus 4. Hopefully you're feeling okay with me skipping the whole FOIL step there, but that's what I have to do because I have a binomial that's squared. A negative out front of brackets, I must apply that negative throughout. So take the opposite of everything inside the brackets. Now I can drop the brackets. Finally, I'll solve. X squared minus x squared is cancelled. So I have minus 4x minus 4 is equal to 100. Therefore, minus 4x is equal to 104. And x is equal to negative 26. Now I'm going to take that number and substitute it back into, we'll plug it into that equation there. So y equals x plus 2. So when y equals x plus 2, I'm going to take and plug in this x value. Negative 26 plus 2. When you add those, you get negative 24. Okay, that was x plus 2. Yep. Okay, so I have an x value and a y value. So the point at which the twos cross, so I could say the solution is they cross at negative 26 and negative 24. And let me show you a graph of what they look like. So here's the hyperbola. You can see the hyperbola, here's the straight line. If I were to take and zoom in a little bit on this part over here, let me zoom in a little bit more, I can start seeing that I've got an intersection point over here somewhere. And I said that that point was minus 26 and minus 24. Minus 26, minus 24. Looks like that intersection point is awful close to what we thought. Okay, so that's an example where it looks like there was just one point of intersection. Here in this line I had shown 2, but when I looked at the graph there was just 1, and algebraically I only found 1. Let's try another example. Solving nonlinear system equations. Here I've got y squared. Ooh, I've got y squareds and x squareds all around. If that's the case, then I'm probably going to go after solving this one by using elimination. Okay, so let's do it. I would first rearrange each equation, and maybe I'll just rearrange the first one so that the y squareds and the x squareds line up. Now what I'm looking for is, so I'm going to use this second equation, and I'm going to use this, this was number 1 rearranged. So maybe I'll call it 1r for lack of a better one. Coefficients the same, coefficients the same. Here I have different signs, here I have the same sign. So it doesn't matter in this case, I have the coefficients the same. I could either add the two or subtract the two equations, and I would eliminate one of the variables. I'm going for eliminating the x squareds, so I'm going to add the two equations since the coefficients are different. 4x squared plus a negative 4x squared is 0. Y squared plus y squared would be 2y squared. 4 plus 4 is equal to 8. Okay, now I've got a simple equation. I can solve it for y. Y squared is equal to 4 when I divide both sides by 2. Then y is equal to a plus or minus 2. Notice that I had to put both of those. When I'm doing a system, I'm going to need to use both of those. Okay, so let me go down a bit. One of the equations was y squared minus 4x squared is equal to 4. That was equation number 1. And what I'll do is I'll just plug in one of my values there. So I'm going to plug in wherever I see a y, I'm going to plug in a, say we'll use a positive 2. Squared minus 4x squared is equal to 4. Let's go down a bit. So 2 squared was 4, minus 4x squared is equal to 4. Move the 4 to the other side. Oh. And subtract, so that would be 0. So divide both sides by negative 4, I still get a 0. And take the square root of both sides, I still get a 0. So when y is the point that I'm going to get from this side, when y is a positive 2, x is equal to 0. Now I can do the same thing and plug in the other value. So I have y squared minus 4x squared is equal to 4. Wherever I see a y, this time I'm going to plug in a negative 2. Notice in this case that it doesn't matter if it's negative or positive. When you square it, it'll be positive. And I get the identical equation as I had here. So I know my answer in the end is going to be x is equal to 0. So again, my point is when x is 0, y is a negative 2. But in this case, I've got 2 points at which these two equations here cross. One of them is a hyperbola, so a hyperbola looks like this, and one of them is an ellipse that I think it looks like this. So, and I'm not exactly sure where they cross, but I think it's something like that, where they cross there, or they touch there, and they touch there. So there's 2 points at which the hyperbola and the ellipse cross. Okay, that gives you an idea, and I've given an example of substitution and elimination. That gives you an idea of what you will look forward to when you're solving nonlinear system of equations. Practice that substitution, practice the elimination, and as you get harder questions, make sure you're keeping track of your pluses and minuses. That's a big thing that messes people up in this section. All right, thanks.